All right, guys. So it's a little bit after 7. We'll go ahead and get started. Welcome to the February meeting for HAL. Not February, it's March. It's later than I think. And I think we've got a pretty nice program here this evening. We'll be doing the agenda. We're going to do the Welcome and Introductions, Book of the Month, our events calendar, some kudos, and then we'll have the presentation with Kalée Tock, and we'll have a few more things with Shallow Skies and some member astrophotos. We got a lot of astrophotos in, which was kind of nice. I didn't think we would have that many. All right, so first off, anybody here in the room new to HAL that's joining us for the first time? Nope. How about online? Do we have any new members online?
I guess I am.
Well, you're not a member, but yeah, no, sometimes we have new members and we like to take a moment to find out more about them. But I guess this evening we don't have anybody new. So. All right. So Dave, are you on, Dave, for the book of the month? Oh. I told you last month that I'm going to do this a lot until I get the names and the faces totally together. Come on.
Okay, some of you may or may not have read this. It's like the only authorized biography of Neil Armstrong that he participated with the author, and of course you've got to help control the narrative as much as possible. Very, very well written, very interesting. A lot of the unknown facts in terms of why he was chosen to be first out, not Buzz Aldrin, which I think probably today Buzz Aldrin probably still a little bit sore about that, but also goes into each of the three of those backgrounds. And there's an entire chapter here that just refers to them as being amiable strangers. Like they weren't buddies. They were good colleagues. They respected each other. They got along well, but probably would never really call them necessarily friends. Like I said, it's very, very well done. And of course, I'm partial to Neil Armstrong as well as the Wright brothers because they both came from my home state of Ohio. So those the famous people that came from Ohio. And one little story that is in here that I like to share, which is quite humorous. Reportedly, after Neil and Buzz got back into the lunar module, they reportedly said, "Good luck, Mr. Gorski." And supposedly, when he was a boy in Canada, his next door neighbors were Mr. and Mrs. Gorski. They were immigrants. He's out playing in the yard, and all of a sudden he hears an argument. She says, "Sex? You want sex? You'll get sex as soon as that boy up there walks on the moon." So again, it's a really, really well written book. This, I think, is what's called the 50th anniversary edition. It came out before Neil passed away, so it was updated with a lot of things that happened afterwards with this. But yeah, highly recommend. I'm looking for a biography.
Thank you, Dave. And just a general plug for the HAL Library that Dave is managing. We've got lots of great books there. And you can go online and see a listing of the various things that are available there. So, you know, if you are interested, you can certainly check out the HAL Library.
One more thing, the book is much better than the movie.
Okay. All right, so star parties, the weather, the ice is finally melting, and we have some events scheduled. Jose, are you happen to be on tonight? I know you're not in the room. All right, so basically this weekend, I think Ernie is the one hosting it. We have our members only star party. So these are, for those of you that have not been before, these are out at Alpha Ridge at the Halo Observatory. They start at about sundown and they usually will run till 11 or 12. It will go later, I think, sometimes if a key holder wants to stay later and it happens to be a good evening. So the first one of the season kicks off this coming Saturday. And then 2 weeks later, on March the 28th, we will have our first public star party. Public star parties are really a great outreach for HAL. They also are really one of the main ways that we attract new members. So if you can make arrangements to be out there with your telescope or your binoculars and just help acquaint the public with the sky, that's a great thing for HAL. And I think a lot of people enjoy doing that, actually. So, keep that in mind, maybe mark that on your calendar. And then looking forward, on April the 18th is the next members only, and April 25th is the next public one. We did have several impromptus. There was one, I think David may have led on earlier this week, I think Monday night. Monday night was just a gorgeous night. I don't know if you guys were out observing or not, but it was just first time you didn't have to be all bundled up, and the sky was really transparent and the seeing was halfway decent. So apparently we had 20 people show up for the impromptu. That's great turnout. And I think David said that there were actually 5 sea stars running from different people that night, which I think speaks a lot to, 3 years ago, we didn't even have sea star. And it's really just these AI type of scopes are really, I don't want to say taking over, but they're certainly having a significant impact in terms of how people are doing their imaging. March the 1st, I think it was the cold night, and Ernie was the only one who showed up. I think he called it, and he was the only one that actually attended. But then back on February 13th, we had another pretty decent impromptu where we had 14 members show up. So again, if you're new and you're not familiar, the impromptus, you have to sign up. You have to go to the HAL website, and you have to opt in. If you do that, then when a key holder sees a nice evening coming up, they will announce on that particular listserv, hey, we're going to go out to Alpha Ridge this evening, and people can join him or her as they open up Alpha Ridge. But again, you have to opt in order to be getting those sort of announcements.
Hey Jim, just to let you know, there was actually 2 in a row this week. There was one Monday night and Tuesday night. Jose opened again, so and I think he had 6 or 7 people on that second.
Wow, you had 6 or 7 on Tuesday too. Okay. The bottom line is that impromptus are a really nice benefit of being a HAL member. You have to be a HAL member in order to participate. And I strongly encourage folks to, if you enjoy going out and observing, Alpha Ridge is got fairly good horizons. It's not, we don't want to call it a dark sky site, but it's certainly got less light pollution in some areas, certainly compared to Baltimore or Columbia. All right, so we have an outreach opportunity that is coming up in the fall. This is the Astronomy Festival on the National Mall in DC. HAL has attended it, I think, for 2 years in a row. And this is one of the largest and most visible public astronomy outreach events in the US. We're going to need 2 to 3 people who are going to commit to staffing a table and setting up for telescope views of the sun and bright evening objects. And I think I've got one person who expressed an interest already, which is great, but we need probably a couple more people. Victor, do you want to say anything about this since you attended the last 2 years? I know you can't make it this year, but can you kind of talk about this particular event and why people might be interested in going?
It's just there are a lot of booths set up with from all sorts of different organizations. It's fun to walk around and look at other people's booths too. And if you like outreach, you can, like that picture up at the top, I'm sort of like just left of the Capitol building. I'm there with my 11-inch SCT. Yeah, right there. And I asked my daughter to take a picture, and of course she picked like the worst time, because the rest of the night there was like a line of 20 people at my scope for most of the night. and Jupiter was out and got lots of oohs and ahs. Could actually see M13, the Hercules cluster. But it's just a good opportunity to have exposure for the club and to talk to a lot of people. This last year, this gentleman was walking around as Galileo. He was speaking with the Italian accent and playing the role. It was kind of fun to see him. But yeah, it's just basically a big star party event. The skies aren't the best, but I think this year there'll also be some ability to see Jupiter this year too, I think.
I think actually you'll
Or
probably have Saturn.
Saturn, I'm sorry.
Not Saturn, but not Jupiter. But can you also talk a little bit about the logistics about how difficult it was or how easy it was for you to take a telescope down there?
So they have it, you can they close off the road, right? That you can sort of see where the crosswalk is. You can pull up your car and unpack all your stuff, and the organizer will get you a free parking pass at a hotel like a couple of blocks away. So what I did was my kid was there, daughter in high school. She sat with I dropped off my gear. She sat with it and just watched it while I parked the car, came back, and it's a little walk, but it's not a big deal. It's and and they have there's no power, so you have to bring your own power supplies. And we could set up a table with our HAL swag. You can see Arjun there with his solar system. Yeah, Crystal was there both years as well, and yeah, it's just a good outreach. There's lots of people who you wouldn't normally see at a public star party. There's, in addition to people who come out for the event, there's just lots of people walking around in DC who are just getting exposed to this is their first exposure to astronomy. So you get lots of oohs and ahs and just good exposure for the club.
Awesome. Alrighty, thanks. And having a couple people there, 2, 3, maybe 4 people, it also kind of allows you to give somebody a break. That you can take turns manning the table or doing the views of what's up in the sky or whatnot. So at any rate, if you need more information or if you are interested in doing this, I don't think I put the date here. Oh no, I didn't up top. It's September 26th. We have an email address. This goes to Mike Miller, who basically coordinates our outreach efforts. So you can send an email to outreach@howardastro.org and let us know that you're interested in participating in this. That would be great.
Hi, Walter.
And so now we want to take just a moment to congratulate Arjun. Arjun gave us a great talk last month about his time doing pulsar research out at Green Bank. And lo and behold, this month's issue of the Reflector, which is everybody, if you don't get the physical copy, you should be getting at least the digital copy as a member of HAL. And in this issue of the Reflector, there is an article by Arjun, and he affiliates with the Howard Astronomical League, and he basically kind of does this paper, which is kind of a recap of what he presented to us the other month. So again, we're just very in awe, Arjun, of your continued achievements. And, it's just really a delight to see how you are increasingly engaged in astronomy and studying it. And you just continue to amaze everybody. So hearty congratulations to Arjun for this accomplishment.
Thank you so much.
Okay, so we're about ready to have our presentation for this evening. Our presenter is Kalée Tock, who is a member of AAVSO, the American Association of Variable Star Observers. That is, I think, one of the oldest amateur astronomy groups and very, very active. She is a science teacher at Stanford Online High School, and she basically is bringing NASA projects into student research. She's been a contributor to the NASA Exoplanet Watch and involved in observing, mentoring, and supporting exotic training. And exotic is free software that helps observers turn their raw images that they've captured of an exoplanet transit into a clean light curve. Almost sounds a little bit like kind of how Arjun last month was talking about refining his data. She is a citizen science contributor to NASA's Pandora mission, which just launched, I believe, in January, and is supporting ground-based transit observations. And Kalée also co-authored a peer-reviewed exoplanet research paper, which helped to demonstrate the value of small telescope follow-up. So, Kalée, I'm going to stop my share and then allow you to share. If you make a request to share, I'll have to grant it here.
There you go. Thank you so much for the kind introduction. And I'm so thrilled that Dale Gent is here. Dale has actually supplied me with many exoplanet transits that I've used and that my students have used in our studies. So I will share a portion of screen. Here we go. Whoa. There. Can you see that?
I think we see it fine here in the room, but you guys online seeing it okay?
All good?
Sure
Awesome.
can.
I think we're good.
Yes.
So I'm Kalée Tock. I'm going to start by introducing myself and telling the story of my journey to astronomical research. And then by the end, if all goes according to plan, we'll end up on an exoplanet far, far away. So here goes. When I was young, I didn't think of myself as a science person. In fact, I wanted to be a minister. I kept taking religious studies classes in college, even after I moved to a concentration in chemistry. And then after college, I started in the PhD program for chemistry at Stanford. But within about a year and a half, I figured out that I enjoyed the teaching part of grad school more than lab work. So I spent a couple of years during which I was still technically part of the chem department, but I was taking classes in lots of different things like computer science, philosophy, and education. And I funded those by taking a job as a teaching assistant for an interdisciplinary course called Light in the Physical and Biological Worlds. And one of the lab managers for the course was, and still is, I think, a developer of exhibits for the Exploratorium, a science museum in San Francisco. And her passion for science and her sense of fun were really inspirational for me. So I transferred to the Stanford School of Education. I earned a second master's degree there. And on the side, I taught chemistry and physics for the Princeton Review's Medical College Admissions Test prep course, the MCAT, which was sort of fun, but I really missed doing hands-on labs. And I had an internship on campus that later became a job doing data analysis for what was then called the Education Program for Gifted Youth. During these years, I got married and had 3 babies who, as you can see from the slide, are not babies anymore. But the education program for gifted youth spawned Stanford Online High School, which is where I now teach. And there was an announcement that came around to a staff mailing list. They were looking for a chemistry instructor, so I knew I had to apply. And I loved it. I taught general science and honors chemistry at OHS for several years. And I've always really enjoyed interdisciplinary science. And I've had a recreational interest in astronomy. And then about 10 years ago, I kept on saying, if English gets to have eclectic classes like film studies, science should get to have eclectic classes too, like maybe astronomy. And so then about 10 years ago, I was told to stop complaining and put my money where my mouth was. And that was the beginning of this intellectual odyssey that has been so formative for me and has taken me to strange and beautiful places I could never have imagined. My career as an astronomy instructor launched along with the first in what would become a series of 4 high altitude balloon launches, which could be the subject of their own talk. But I believe that science in general and astronomy in particular scratches that same itch to ask big questions that brings people to church. So I have fulfilled my childhood ambition, even though my ministry is not at all what I would have originally envisioned. Teaching and learning about how the universe began or didn't, or what the implications would be if we find evidence for life on an exoplanet, just strays unavoidably into philosophical territory. So on the slide, we see the pale blue dot, which is the last glimpse of our planet by the Voyager spacecraft on its way out of our solar system. Voyager was launched in 1970s. It's traveled over 16 billion miles, still only a tiny fraction of a light year, but it's the most distant human-made object. And on its way out of our solar system, it snapped this picture of Earth before our planet was forever lost to its view. And when contemplating this, Carl Sagan famously described our planet as a pale blue dot suspended in a sunbeam. So, what can we learn from a pale blue dot? Well, we can learn whether there are clouds or potentially oceans. Over 24 hours, we might see variability due to different fractions of land versus oceans. Over 360 days, we might see it block the light of its host star, our sun. We could do atmospheric spectroscopy to get a clue whether this pale blue dot has very much oxygen or methane. And we could tell whether there are plants by the color of the dot. And maybe you don't think of plants as blue, and they're not. We commonly think of plants as green because they reflect green light. But if that's the criterion, plants aren't green, plants are infrared. They reflect much more infrared light than they do green. So if we could see in the IR, we could tell by the color of our planet that we have plants. And that's, of course, why IR is a great region of the spectrum to study exoplanets. It's why the James Webb Space Telescope, which uses infrared cameras, is so valuable for doing so. But even James Webb Space Telescope has a hard time seeing the pale blue dot directly. Usually it does the same thing we do from the ground, which is take images and spectra as the planet transits its host star, looking for clues about the planet from subtle features in the dip of the starlight that it blocks. And for this to work, the planet has to block starlight from Earth's perspective. So it has to cross between Earth and the star during the orbit. And then how this dip looks, how flat the bottom is, how it goes into the transit and comes out of it, can yield lots more details about the planet and many more also about the host star itself. So the easiest planets to study with modest-sized telescopes are the planets that orbit frequently, where frequently means every few days, and make big dips, where big means that they decrease the observed brightness of the star by 1% or more for a few hours during the transit. So to orbit frequently, by Kepler's laws, they have to be close to the host star. And to make a big dip, they have to be big, like really big, like big as Jupiter big. Jupiter's radius is 1/10 of the sun's, and area goes as radius squared. So if you divide the area of Jupiter by the area of the sun, it'd be 1/100th or 1% of the light being blocked. So you need a Jupiter, but you need one that's close to its host star or a hot Jupiter. And hot Jupiters are weird because they tend to be made of ice and volatile molecules, the kind that are typically blasted far away from the star after it ignites because they're light and vaporous. And they're not thought to be able to accrete into the core of a planet close to a star. So the big question is, what are they doing there? In our solar system, gas giants are found in the outer solar system where they belong, but extrasolar systems seem to have a lot of gas giants that are abnormally close to their host star. And one possible explanation is that they form farther out, but then they collide with stuff and lose orbital energy and migrate inward. Or maybe they're actually really rare and they only form under very unusual circumstances. And the reason we see so many of them is that they're easiest to see because they're big and they transit often. Because you need at least 3 transits to confirm an exoplanet, and the first exoplanets were discovered in the 1990s, so you can do the math on that. In our solar system, Jupiter has a 12-year period, Saturn has 29 years, so it would take 24 years to confirm a normal Jupiter-like planet if we were lucky enough to see a planetary transit right when we started looking in year 0. And it would take 58 years to confirm a Saturn using the same logic. So there might be like bazillions more normal Jupiters and Saturns out there than there are hot Jupiters. We just haven't confirmed them yet because we haven't been looking for a long enough time. We really don't have a good feel for the statistics of this and how much our selection bias toward things that are easiest to see influences our inferences about things that are out there. But whatever the statistics may be, to figure out what's going on with these enigmatic hot Jupiters, we have to study them. And that can be done and is being done in space telescopes, but small backyard telescopes are also essential to the process. This is one of my former students, Jana. And we said that hot Jupiters have short orbital periods, like a few days, but if the orbital period is off by small amount, like if it's off by only 10 seconds or like 0.0001 days, then over 10 years or so, because it's going every few days around, the mid-transit time might drift by as much as several hours. And if we point at the target several hours too early or too late, you'll completely miss it. So we have to keep observing transits to keep NASA's prediction of the next transit time, what we call the ephemeris, fresh and accurate. I see a hand. Can I get a question? Go ahead.
When you're using the transit method, what happens if the planet's plane is not what if the plane of the planet is not like parallel to our telescope?
That's such a great question. If the planet's going around in a plane that's perpendicular to our line of sight, we don't see it transit at all. And if it's inclined a little bit, we could maybe see part of it transit. And that's called a grazing transit. And they're really hard to analyze because you have to know exactly how much of the star's light is being blocked. But if there are many cases in which we wouldn't see it at all. So that's another way in which we're having some selection bias. That's a great question. Thank you so much for asking that. So in any case, at this point, there are thousands of known exoplanets that transit that to keep track of. So it's too big of a job for any one observer or even any one space agency to do alone. In other words, NASA relies on amateur astronomers and school groups to keep making the measurements. And there are uses for continued measurements even beyond keeping the data fresh and the ephemeris fresh for space telescopes. and large ground-based telescopes. For one thing, there are TTVs. If we measure a transit and then the next time we measure it, it's late based on the orbital period we've calculated. And then the next time it's a little less late, and then it's early, and then it's less early, and then it's late again. That's what we call a transit timing variation, or TTV. And TTVs might happen because the planet's being pulled by something, like maybe a moon or another planet in the system, and we might not see the object doing the pulling because it's too small, or it hasn't transited yet, or its orbit is not in a plane between us and the star. But we can tell it's there because it affects the transit midpoint of the object we're measuring. Even variations in the transit duration or the length of time the planet spends transiting can indicate the presence of another planet in the system. So this is the blue planet that's going to affect the red planet's mid-transit time. And because the blue planet is there, the mid-transit time of the red planet isn't exactly on the time we expect it to come in. That's what this animation is showing. So if we have a lot of transits of the red planet, a lot of transit midpoints measured, we might be able to see that it's happening right on time, and then a little bit too late, and then a little bit too early, and so on. But we need a lot of transits in order to make that measurement. The second reason why the planet's mid-transit time might vary is called apsidal precession, which is an effect of the warping of space-time near a large mass, like a star. And this is caused by relativity. It's a prediction of Einstein's. And we've actually observed this in our own solar system with the planet Mercury, which is close enough to the sun to exhibit this effect. And hot Jupiters are really close to their host stars, as we've said. They have to be because they're orbiting so quickly. So their orbits are also predicted to precess because of general relativity, and the slight variations in their mid-transit times provide some evidence that this is actually really happening. And then the last reason, or the last reason that I know of, I'm sure there are more, why a planet's mid-transit time might vary is that its orbit is decaying and the planet's in the process of spiraling in toward its host star. And this is more common with hot Jupiters because they're close to their host stars to begin with. And because they're so close, the difference in gravitational attraction between the near side of the planet and the star and the far side of the planet and the star is big. And the difference in gravitational attraction is called a tidal force, and it causes the planet and the host star to distort and oscillate. And that gradually converts the planet's orbital energy into heat within the star, and it also exerts a gravitational torque on the planet that causes its orbit to decay. So we can tell that that's happening again by these TTVs, these transit timing variations. So they're interesting and useful, but finding them takes a lot of astronomers measuring a lot of transits, which brings me back to why we've got to keep observing these exoplanets and contributing as much data and analysis as possible to NASA. So let's do it. You can search up the Swarthmore Transit Finder and enter your latitude and longitude and specify you want at least a 1% transit depth or 10 ppt because they do things in parts per thousand on that website. It'll show you all the planets that will be visible from your location for the next 3 nights. It tells you when to start observing in local time or in UTC if you roll over this time window. And when I looked on the HAS website, it said you often observe at Alpha Ridge Park on Old Frederick Road. So I put that in, that latitude and longitude. And so from this screenshot of the Swarthmore Transit Finder output, you can see that if you teleport there and start observing right now, or in 17 minutes at 7:57 local time, you could catch WASP 65b, which is a magnitude 11.9 planet that has a depth of 12.8 parts per thousand or 1.28%. But if you need more than 17 minutes to get set up, you could try for Kelt 23 AB. And you would need to start observing for that one at 12:18 a.m. to get an hour of baseline. That's the standard. We want an hour on either side of baseline before Kelt 23 AB's ingress into transit begins. And then by sunrise, you'll just, like right at 6:41, you'll just be wrapping up the post-transit baseline. And it actually tells you can't really see it on this screenshot, but the line starts getting dotted when the sun comes up because they know you can't observe then. So anyway, though, if you need your beauty rest, there are a bunch of robotic telescope networks. If you're a member of the AAVSO, the American Association of Variable Star Observers, you automatically have free access to AAVSOnet, a worldwide network of research-grade telescopes which operates on a proposal system. Alternatively, my colleague Michael Fitzgerald hosts a network called Next Astro, but that's not free, but it has a lot of other resources in addition to telescope time. And if neither of those work for you, Exoplanet Watch has a free data checkout system hosted by the Harvard-Smithsonian Micro Observatory that you can use, which brings me to AAVSO and Exoplanet Watch. NASA can't store all your images. Those image files are enormous, like hundreds of megabytes each sometimes, and all astronomers store data in different formats, and every astronomer thinks that every other astronomer's formats are wrong. So rather than several gigabytes of images for differently formatted transits, what important information does NASA need to store? Well, it needs to get the shape of that light curve. So it needs a text file that stores 4 numbers per image. You need the time of the image, the light from the star, and 2 numbers describing how much of Earth's atmosphere went through or the air mass. And AAVSO maintains a database of exoplanet host star observations for NASA Exoplanet Watch. AAVSO is a worldwide scientific and educational organization of amateur and professional astronomers who are interested in stars that change in brightness or variable stars. And that might happen because of stuff happening inside the star or because a planet or something else is blocking the star from Earth's line of sight. And membership is open to anyone interested in contributing to variable star research. Professional astronomers don't have the time or the telescopes needed to gather data on the brightness changes of all of these thousands of variables. So amateurs make a real and useful contribution to science by observing variable stars and submitting their observations to the AAVSO International Database. So if you want to contribute exoplanet transit data to NASA, make an AAVSO account, request an observer code. That part's free. You don't have to join AAVSO to make an observer code. You do have to join to use their robotic telescope network, but you don't have to join to make an observer code. Membership for students is discounted, so you can keep that in mind, the students on the call. But let's say you get images from somewhere. You get them from AAVSOnet or from the data checkout system, or you head out to Alpha Ridge Park right after this talk and get the images, or you talk Dale into getting some for you, which I've done many times successfully in the past. Thank you, Dale. Next, you have to find the star in the images. So here's an image, for example. Do you see the star that has a planet going around it? No? Okay, so we have to identify the target, and there are several ways to do that. You could plate solve it and then mouse around until you're on the right coordinates. But the way I use with my students is to go old school and match them up using a star chart from the AAVSO. This is the variable star plotter, or VSP, and it plots the stars in a region that you define using the coordinates of your target. So you can look for patterns and asterisms and match up the stars. And I've looked at this star field a few times, so it kind of jumps out at me that these 4 stars match up with these 4 stars, and from there I can do what's called star hopping to find my target. And I'm sure many of you have done that with targets you've looked at before, but it takes a little while to get used to doing it, which is why I use the star chart method with my students. So it's right there. The yellow shows the region of the star chart, and it wasn't rotated or flipped, which is helpful because sometimes it is. But now we just have to find that in every one of the hundreds of images we've collected and measure the star's light or photometer it. And then we can plot the photometry of the star as a function of time and look for the dip when the planet passes in front of it. But it's not exactly that simple because our own planet is spinning. So from the perspective of the telescope, the star might be getting closer to the zenith or the highest point in the sky, or it might be getting closer to the horizon. But either way, it's not going to be staying in the same spot. If it's getting closer to the horizon, then it passes through more air on its way to our telescope, and that makes it dimmer and redder, the same way the sun looks dimmer and redder near the horizon. And if it's getting closer to zenith, it'll look brighter and bluer. And all of that means that if you just plot the brightness as a function of time, you'll get something that looks like this. And there is a dip there. You can see it if you know what you're looking for, but we're not interested in how the Earth's atmosphere was changing. We're interested in how the star's light was changing. So we have to correct for the air mass. This is why exoplanet astronomers are kind of obsessed with air mass. And that's not the only atmospheric effect to correct for. Maybe there were some high, thin clouds that rolled in during the observing run that were invisible to the naked eye. Maybe they only affect the light of the target by like 2%, which is about, oh yeah, the amount of the dip we're looking for. So to correct for all those other atmospheric effects, we use a comparison star or comp star, which I'll talk about more in a sec. But in any case, if we do all the corrections properly and we pick a good comp star, we can turn the plot there into something that looks a little more like this. But to get to this, we have to explain what a comp star is and how to pick a good one. As we saw here, if we just plot the flux, we get a wavy line. But another star that was next to our target star was having the same increase in flux over the course of the observing run. But for that other star, there wasn't a dip. It was more a straight line. So we can compare those two, and then we can really tell that the target had a dip and the comp didn't have one. And there's lots more to be said about calibration. But for now, we can just make sure that the comparison star is not itself variable by checking the variable star plotter on the AAVSO and looking for stars with little numbers on them. Because we don't want our comparison star to be variable, because if it's getting brighter or fainter, having its own exoplanets or something, that might interfere with the signal we're looking for. And AAVSO has kept some records of stars that have been observed to be relatively constant. It puts those on the variable star plotter charts and labels them with numbers corresponding to their brightnesses times 10, so they don't have to put a decimal point, because that looks kind of like a star itself. But any star with a number in one of these star fields is a recommended comp, and that means that it's one that's been studied. So you found the target in the star field labeled in green on this inverted image, and you chose a few comps which are labeled in red. And now you need to define the same region around each one, that's called an aperture, and count all the photons that struck the sensor within the circle. And then you need to do the same thing for each of a couple of hundred images in your series. And then you need to take the ratio of the brightness of the target to the brightness of the best comp for each of the images and plot that over the course of the entire observing run. Don't worry, I was kidding. We have software for this, and that's called Exotic. Caveat that you don't have to use Exotic. If you do this sort of thing on a regular basis and you use software like Astro-Images or DS9 or Afterglow, you can use any of those that you like. You just need those four numbers: brightness of the star, time, and those air mass parameters. And the brightness of the star should be compared to a comparison star that's stable. But the power of Exotic is that it's built especially for this. It runs directly on your images and it can do that in the cloud. You do have to find your target in comps in the first image of the series. And so instead of specifying them by right ascension and declination, you specify their pixel coordinates in X and Y on the image. And then you just do that on the first image of the series. And Exotic has algorithms that will follow the stars whose pixel coordinates you specify through the rest of the images, even if they're not plate solved, as long as the telescope doesn't move too much between the images or you don't have clouds for too long. Actually, Exotic's really good. It can even handle it if the telescope does a pure flip most of the time. But yeah, the idea is we try to keep it as stable as possible, as I'm sure you're aware. So then to fit the light curve correctly, Exotic needs information about the observatory your images come from. It needs a bunch of other information, like what kind of filter was used, because the transit might look very different in very different filters. And then it also needs information about the planet, like its known transit depth, duration, the shape of the curve, a whole bunch of information about the properties of the host star. And that's because the light curve that Exotic generates uses what's known about the host star and its planet to inform the priors of the fit. And the priors are parameters that define what the light curve is expected to look like based on what's already known about the system. So that gives it a starting point for fitting, how sharply the curve dips, how flat the bottom is, how long the eclipse lasts, all that stuff. And once it finishes fitting your data, it generates a data file for you to upload to the AAVSO exosite that has all the times and brightnesses and air mass parameters and such. And the midpoint of the transit on the night you took your images will be one of the posteriors that will in turn inform the priors Exotic uses for future fits of the same system. And Exoplanet Watch uses the analysis of observers like you to update the priors for every exoplanet system every few days. They literally take all the data that has been submitted and rerun everything. They rerun all the fits with updated priors so the posteriors can be known as precisely as possible. Hand from Victor. Go ahead.
Thanks. What makes how do you get the error bars on each point? What determines that?
That's a great question. Exotic has so Exotic's algorithm finds what it has an optimal aperture photometry algorithm. And it finds the optimal aperture for the target and the comparison stars based on your images. It reports that in one of the output files, and then it uses that for every point and generates the error bars internally. However, sometimes it determines in its wisdom that point spread function photometry is more appropriate. I'm assuming based on the question that you know what PSF photometry is, and so it then runs a different algorithm with a different error calculation method. And I don't know the details of either of those error calculation methods, but I know that there's a lot of thinking went into them. And if you ask on the Exoplanet Watch Slack group, I'm 100% sure that you would get more satisfactory answers to how those error bars are determined. But thank you for the question. And sorry, I can only partially answer it.
Thank you.
Sure. So they literally refit everything every night. Every single transit that's been uploaded is going to be fit again and again and again. every few days to make the sure that the posteriors are known as precisely as possible so that they can inform future priors of the fit. But one thing that prevents the uncertainty from getting as small as we might like is the host star. Pretty much all stars are variable at some level. They can swell up and shrink down and change color and orbit companion stars and rotate and have starquakes and star spots and all sorts of things that make it really hard to know which part of the brightness change we observe is due to the planet blocking it and which are contaminants, that is to say, other stuff. And the mantra is know thy planet, know thy star. And there's a mission that just went up last month called Pandora, which is, I think its commissioning phase is over, and it might be actually taking observations now, but it might still be finishing up the commissioning phase. And it's called Pandora. And it has a 0.45 meter telescope in low Earth orbit that can do visible photometry and infrared spectroscopy. And its goal is to disentangle star and planet signals in transmission spectra to reliably determine exoplanet compositions of their atmospheres. And this is broken into two goals. And this is a quote from the Pandora website. The first one is determine the spot and faculae covering fractions of low mass exoplanet host stars and the impact of these active regions on exoplanetary transmission spectra, which is a fancy way to say find the star spots. And then the second one is to identify exoplanets with a hydrogen or water dominated atmospheres and determine which ones are covered by clouds or hazes. So it's going to observe 20 exoplanets over long durations, 10 transits per planet approximately, and their sizes range from Earth size to Jupiter size. Their host stars span like mid-K to late M spectral types, and the target list is published right on the website, which for some reason isn't showing on my screen share, but it's down at it's very easy to find, pandorasat.com/targets. And they need simultaneous ground-based observations of these targets, both in transit and out of transit, because long-term baseline variability is needed. So they're looking for rotation rates and star spots, and those tend to show up well if you use different filters at the same time. So I currently have a team of students in my research seminar working on looking for star spots right now. And any observations you upload to AAVSO will automatically become part of the set. And anyone who uses your analysis in a study then must invite you to be a co-author on their paper. So when you upload data to AAVSO, it's listed under your AAVSO observer code rather than your name for privacy reasons. And if you want to collaborate with another observer whose data you use, there's a collaborate button that sends a request to AAVSO. So a while ago, my student Alex received an email from AAVSO asking if he'd like to collaborate on a study that was using data from a transit he had analyzed and uploaded of WASP-77AB. And the email had an attachment from someone at Arizona State University named Fred Nuger, and Alex said he was interested. And after that, it was only a few months until publication, and Alex said he got regular updates as to what was going on with the project. He had an opportunity to review the paper and offer any feedback on the draft before it was submitted. And needless to say, he was thrilled by this fortuitous co-authorship. And one of the many things that I love about Exoplanet Watch is this culture that they've cultivated of sharing credit with everyone who contributes. And that could be you. So I hope some of you will consider joining the vibrant and active Slack channel of NASA Exoplanet Watchers. They're relatively easy to find. The group is super fun. I guarantee they will have detailed answers to Victor's error bar questions. There's a special beginners channel for people just getting started. There's a book club. We're currently reading Project Hail Mary. And Tuesday trivia at Wildlife Wednesdays and an active astrophotography channel. Rebecca Black memes every Friday. When you ask a question, people answer. When you post your first light curve, you're guaranteed to get several celebration emojis and words of encouragement. This community is welcoming and collaborative and supportive in exactly the way I think science is supposed to be, but often isn't these days. And so as a teacher, I feel really good about sending my students there to ask questions and engage with astronomers who are more experienced and knowledgeable than I am. Now, as we've said, all the planets we can image from the ground are hot Jupiters. They're gas giants that are close to their host stars. These are not rocky Earth-like worlds. So why do we care about them so much? Why do we need a citizen science project of such enormous proportions to study worlds that are too extreme for life as we know it anyway? Well, first, we don't yet have the technology for rocky Earth-like worlds. Those are hard even for James Webb Space Telescope. Our planet's too small relative to the sun. It blocks too little of its light. It orbits too infrequently. NASA's next flagship mission, the Nancy Grace Roman Space Telescope, will pave the way for possible missions even farther in the future, like the Habitable Worlds Observatory, and those will hopefully image and characterize Earth-like worlds around sun-like stars. But, we have a lot to learn from hot Jupiters. As we said earlier, their very existence in this unexpected position close into their host star challenges our theories about how planets form in the first place, and the chemistry of their atmospheres teaches us all sorts of things about planetary science, and some of those might be relevant to the future of our own planet. And their orbital properties teach us about tidal forces and general relativity. And who knows, maybe the properties that make hot Jupiters too extreme for life as we know it actually make them well suited to life as we don't know it. Also, studying hot Jupiters will pave the way for our ability to find and study planets a little more like our pale blue dot. So I'll finish with Carl Sagan's pale blue dot video, which is probably something you've seen before, but I think you'll agree it bears a rewatch every now and then. So here is Carl Sagan, and I'll finish with this.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on the mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they can become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the faithful dot, the only one we've ever known.
I've seen this video so many times I could recite it, but it still gives me chills every time. So powerful. In any case, thank you so very much, and I'll happily take any more questions if you have them. I see there's a question from a high school teacher. Yeah, email me. I'm going to put my email in the chat. And let you know if you're a teacher and want to know how to organize a group of transits for students to run through Exotic. I have a lot of experience with that because I do it twice a year and I always hear about it on my course evals, how wonderful they found it. And it's great thanks to Dale and other observers. I didn't know Dale was part of this group, but he has supplied me with very many transits that have made very many students very, very happy to contribute those to NASA. So thank you for that as well. Yeah, and so if there are any other questions, I'll stop sharing and
Well, I have a question. Can you speak a little bit to what sort of telescope size is appropriate for doing this work? And are you just using a standard CMOS camera? Can you tell us a little bit more about the actual nuts and bolts of obtaining the data?
I can only tell you a little bit. In fact, Dale can tell you more since he obtained much of the data that I used. I use robotic telescope networks primarily. I've used Las Cumbres Observatory Network. I've gotten actually a lot of data from just people I know, Dale among them, and people on the Exoplanet Watch Slack group. I'll say like, hey, I need a bunch of transits for my students for this coming assignment. We have one coming up next month. So I've just been finishing up the collection for that one. And then in the fall, I'll do another one, each with about 30 students. So since each transit takes about 5 hours to collect, I get them from anyone who will give them to me. And I don't do the observing myself, so I don't want to put Dale on the spot. But Dale, if you could say any more about your system, I think that would be useful to people.
Sure, Kalei. Great to see you. Yeah, this is kind of like my home club. So, I was really thrilled to see you on the speakers list coming up. Um, the As far as equipment goes, yeah, 16-bit CMOS sensors have been a windfall technologically for opening this up. You don't need the expensive old CCDs anymore. More commodity systems can be used that have the bit depth needed to capture the subtle variations in the light coming in, and the so yeah, if you have a modern IMX 571 or IMX 455 full frame, or even an IMX 533 would do. But you want to have a large chip so that you can get a wide field of view in your image, so that you can have as many comparison stars as possible. So field of view is important. Of course, aperture is important as well. The shallower um, the light dip is, the larger the aperture you will need to resolve that dip. So smaller telescopes are more limited towards more deeper dips in the light curve, which doesn't, does your 3-inch or 5-inch refractor isn't useless here. They're very useful for still capturing these types of planets, but there's practical matters when it comes to just how that delta magnitude is. Um, but that's basically it. And the you fix the telescope on the star, you start imaging it. The cadence can be pretty fast. You usually want an ADU value in the middle somewhere, 50% range. That would be about 32,000, 33,000 on a 16-bit sensor. So the dip will then take that down a little bit, and then it'll recover, and that's what you're measuring. So uh, that's basically it in a nutshell when it comes to the technical side of things here.
Yeah, and I'll echo that. I had a student who got really into imaging, quickly surpassed my own knowledge about the nuts and bolts of imaging, and he had a 3-inch refractor, and was able to capture some good exoplanet transits. Again, looking for, as Dale said, the large change in large dip depth. You want as big as you can get for a smaller telescope, but he got some great transits, super clean.
Yeah. And there's some things you don't do that you would do in kind of like pretty picture astrophotography. You don't dither or anything like that.
Right.
It's just image after image after image after image, and you're just trying to get the highest resolution data when it comes to the curve. So there you go.
Yeah, it absolutely. Go ahead, Chris.
So along those lines, to follow up, if you have a 3-inch refractor, um, is the data that your team and Exoplanet Watch is looking for, is given the small number of stars that have those huge dips, is that still valuable data just because it's easy for cheap refractors?
Everything's valuable. In fact, I try to use transits that have enough of a dip to be significant. But the people at Exoplanet Watch will put up celebration emojis even if the light curve's really messy. And the PI, the principal investigator for the project, Rob Zellum, often says like all data is useful. Because even just informing the posteriors by just a teeny, improving the posteriors by just a teeny bit adds up to either time saved on large ground-based or space telescopes or better information for collecting those transit timing variations, right? Like even if you're one of a handful of people that observed that large planet's transit that night, maybe the combination of all of your data will enable the confirmation of a transit timing variation just because you need so much data for those things. And they have one of my favorite plots that I should have made a slide of on the Exoplanet Watch website on NASA is they show a light curve for a particular hot Jupiter that has contributions of data from all sorts of places. And they have this really cool algorithm where they shade everyone's contributions in different colors. So you can see there's like this rainbow of improvements to the ephemeris over time, which is kind of neat to see. So yeah, I mean, I would say probably the larger planets are observed more, but more observations means we can do more stuff with it. So they're all valuable.
All right, any other questions?
I'm actually queuing up 2 exoplanets for observing tonight right now.
Yay!
Um, I can share my screen and just give a
Please, yeah,
quick rundown if
that'd
that's
be
okay
really
with
helpful.
if
Yeah,
that's
sure. Sure,
okay.
go ahead, share your screen, Dale. Take a couple
Sure.
minutes and show us what you're doing.
Yeah, this won't be long. Let me find the right window here first.
Yeah, I did want
Uh,
to point out, I know there's a lot of imagers in the club that use Nina. Nina has an excellent plugin called the Exoplanet plugin that will help you find those big transits.
and that's exactly what I'm using.
Yeah, see, there you go.
Yeah. So in my Nina sequence here, I've queued up I have 2 templates called Exoplanet. Very original name, I know. But then I pulled down a catalog from Exoclock, actually, in this case, of transits that are happening where my telescope is currently out in western New Mexico. So I've queued up WAPS 65 Bravo there. And over here, it gives us an overlay of the transit when it happens. So the start time here is at 1800 hours local. This is that 1 hour baseline observing that happens before the predicted transit starts, right? So at 1904, at 7:04 p.m., that transit starts. It's expected to reach the maximum depth around 7:25 p.m. That maximum depth continues until about 2100 hours. It slopes back up, and then we have our 1 hour tail on the end of that observation to form that baseline. Now, with this one, you may notice that right now out in New Mexico, it's just past 6 p.m. and it's still daylight outside, and we hit civil and then astro dark not until about 2000 I'm sorry. Um, yeah, about 20 about 8:40 p.m. or something like that. Um, but even partial transits are, my system won't start imaging this until it's after Astro Dark. So even partial transits are valuable. Um, because we start out in the trough and then we expect to see the light come back up to the baseline. So we'll image that to start out. It's the best one out there that fits right now for this night. But then about an hour and a half later, it'll pick up on this one here. It starts at a little after midnight, 12:24 a.m. And it will go for an hour and do the same thing basically. And what's interesting about the exoclock catalog of exoplanets, especially for new people, new folks to this, is that it actually kind of advises you on the minimum aperture required for imaging that transit. So if you're not sure about depth yet, after a while you can look at the depth and magnitude here and just kind of know by eye what works for your telescope or not. You'll always have that, but for the exoclock database, it also gives you this minimum aperture information. So you can kind of learn your system based on that. And there you go. So this drops it off in images. I calibrate them in the morning and then either process them myself or send them on to people like Kalée. So there you go.
Very nice. Thanks, Dale.
Mm-hmm.
All righty. Any final follow-up questions for Kalée? Thank you so much. Great presentation.
Thank you so much for having me. I really enjoyed it.
All right. So guys at home, are you seeing the screen?
Not yet.
Oh, it helps if I do share, doesn't it? Yeah. So let me know if you guys are seeing it yet.
Thank you. Thank you. That was so fun.
Great. Well, it was an excellent presentation. You're a great delivery and fascinating topic. So again, that's just awesome. Thank you very much. All right. Looking ahead to next month, what we're going to do is kind of like a dark skies travelogue. Some of you may know that Victor went, I guess in February, down to Chile, and he had the opportunity to do some observing out near the famous Atacama Desert. And you'll see he sent one of his photos in for this evening's astrophotos, which is just stunning. So he's going to, this is going to be a set of like mini talks. So I think Victor will probably, give us some background on his trip and what he did and, the pros and cons for about maybe 15 minutes or 20 minutes. Then we're also going to have our HAL secretary, Bill, talk about his trip to Mauna Kea and his experience there, which then leads me to, I need a couple more people. So have you been to the Winter Star Party or Cherry Springs or maybe someplace out in West Virginia or someplace out west that was a really cool experience? And you'd be willing to talk for maybe 15 minutes and tell us, what motivated you to go there, how it came about, what equipment, if you took any equipment, any of the logistics involved in that. You don't have to have a bunch of photos that you took while you were there. If you have them, that's great. But I'd really like to get a couple more people so that we can have like 3 or 4 different reports about people visiting dark sky areas. So again, please reach out to me if this is something that you would be interested in helping out with next month. And I appreciate it very much. All right, so we're going to go into our shallow skies portion. So last month we talked a little bit about identifying the constellations, kind of looking to the south. Let's turn around and look north. And in the springtime, if you look around 8:30 and you look to the northeast, what you're going to be able to trace out is going to be the Big Dipper, which of course is one of the most iconic constellations that we got out there. So here is the Dipper, and you can see they're actually, the Dipper itself is what we would call an asterism. the Big Dipper is not truly a constellation. Ursa Major, the Big Bear, is the actual constellation, and you can see here the paws of the bear. And then you've got the Little Bear over here where the tip of the handle is, of course, Polaris. So this is a good, again, for if you're new, trying to get oriented, you want to get yourself a few landmarks in the sky. And that way, as Kalée was saying about star hopping, it's the same sort of principle. You identify certain particular patterns, and you can then go from there to find other patterns in the sky. So this is the Big Bear, and it's always kind of interesting with the Greek mythology. Ursa Major, the Big Bear, is actually Callisto, who was a nymph that served Artemis, the hunter, until she was transformed into a bear by Hera. Hera was jealous. I think Callisto and Zeus had a fling. So years later, Callisto's son, Arcas, almost killed her. He was a hunter and he was out hunting. And he didn't know that the bear was his mother. And so at the last moment, Zeus took pity and intervened, and he lifted them both up into the heavens as Ursa Major and Ursa Minor. So Ursa Minor is Arcas. He's the son of Ursa Major, the Big Bear. And they actually, from our standpoint, are circumpolar, which is to say they never set. And again, part of the myth is that Hera asked Poseidon to not allow them to dip into the ocean. And so they just skim along and then come back up again in the spring. So once you have found the Big Dipper and Ursa Major, one of the things that you can look at is the star at the bend of the handle right here is called Mizar. And there is, if you have good eyesight and a dark sky, you'll also see another very tiny star right next to it, several magnitudes fainter, and that is Alcor. So this is kind of like horse and rider, Mizar and Alcor. And it's a good test of your eyesight if you can pick it out. I'm long past that point. I need my glasses to pick it out, but it's kind of a fun thing to do to see if you can see that little Alcor riding on the back of Mizar. You also, if you have a telescope, and it doesn't have to be a very big telescope, you can examine and you'll see you've got Alcor here, Mizar, but with a little bit of magnification, you'll see that Mizar splits into a double star again. So, and they're fairly equal in brightness. So it's a very cool double star. This ends up being, I think, one of the first double stars that a lot of people turn their telescope to, partly because it's relatively easy to split and because it's relatively easy to find. So this is definitely something, if you're looking to kind of get oriented to the night sky in the spring, start by looking north and trying to identify the Big Dipper. And then if you happen to have a telescope, be sure to check out that star in the handle, Mizar. And there is a photographic image, and you can see Mizar, a somewhat tight double compared to the field, and then this is Alcor. So in a couple months, we're going to have somebody talking about the moon, and I think the moon's going to get a lot of attention this year with the Artemis missions and whatnot. So again, kind of part of the shallow skies, let's talk about a particular feature that you might be able to observe on the moon. This feature this month is Valles Alpes. It's a valley on the moon. It is a pretty straight 100-mile valley. So kind of like a Grand Canyon that cuts across the moon's Alps. In the southern part of the moon is always, you'll see far more craters. The northern part has the impact basins. This particular crater is easily recognized as Plato. It's a fairly large with a very flat plain. And near Plato is this feature that we're talking about. So it formed long ago when the moon's crust cracked and it sank. and then later it filled with smooth lava. So here's the feature here. Here's Valles Alpes. And you can see it really wouldn't take a lot of magnification in your telescope to be able to pick this out. And this is Plato, again, fairly large crater with a flat plane in it. Now there's a second more challenging aspect to the Valles Alpes, and that down the middle, I don't know if you can see hopefully on this slide here, there is a very thin groove called a rill. So there's almost like a very thin channel that runs down here. It's really narrow so that it's a struggle for even larger telescopes to pick up. Probably need at least an 8 to a 10 inch, and you would need a night of very good seeing.
Jim, can I contribute something here?
Absolutely.
So I recently invested in the 3.7 millimeter ethos, which is 100 millimeter apparent field of view, super high power. And I put it on the moon when we finally had a clear enough sky, sat there for 2 months, in the box.
Right.
And when you get that large a field of view and that magnification, got my 5-inch, my 1100 millimeter focal length refractor, it was blown away. And I was so unhappy that I was alone at my house because my wife's got zero interest.
Yeah.
But nobody would have left the eyepiece. It is unbelievable. So I'll have it out there, if the star parties are clear skies. And I tell you, there's still nothing like looking through the eyepiece.
Yeah, absolutely. I know we've gotten
is
very much into imaging everything. And I love C-Star, but I mean, to me, the fact that you can't ever look through the thing kind of.
Yeah, but this is like an unbelievable, it's like shocking.
Yeah. Oh, that's awesome. That's great. I'll look forward
The
to
resolution.
maybe getting a view through it. Yeah,
I look forward to seeing that.
Yeah, the resolution is just like unbelievable.
very cool. So basically, there's a challenge object there. If there's a little bit for everybody. If you have a smaller telescope, just see if you can pick out this Grand Canyon on the moon. If you have a larger telescope and you can crank up some power and you have some steady seeing, take it as a challenge to see if you can find that little rill that runs down the middle of it. Okay, as with so many things with the moon, the lighting is really important to get your best view. So the optimal dates are coming up. I think this is like 2 days before our public star party, March the 26th. That would be in the evening sky, probably close to first quarter. The 8th of April, which would be a morning object, so you would have to get up kind of like a little bit before the dawn or shortly after dawn to try. And then again, April 24th. So again, maybe put that on your calendar and see if you can spot this object. Okay, on to this month's astrophotos. All right, Harini, you are first up. Would you like to tell us a little bit about this image that you took here? Are you on mute, Harini?
Yes, I'm here.
Oh, there you are. Okay.
So this was the Orion Nebula, and this has been processed. So I took my data from my C-Star and then put it into the Deep Sky Stacker, and then after that I went into GIMP and then I fixed all the changes in the gases and like made it more natural.
Very good. You really are progressing, being able to go in and get the images off of the C-Star and begin to manipulate them. You should feel very good about that.
Thank you.
We got one more from you. This looks like the Pleiades.
Yeah, this is the Pleiades stars, and this was an open cluster, and like the Orion Nebula, I also stacked this and put it into GIMP, and then afterwards, I fixed the background so that it was like less brighter, so then it became more natural too.
Karini, do you know how much time you spent, how long that exposure was?
I'm actually not really sure.
Okay. It looks like you put a fair amount of time into getting that because of the nebulosity you got there.
Yeah.
Very nice. Good
Thank
job.
you.
Wes.
Yeah, so this is a picture through my Daystar quark on an 80 millimeter telescope. So it's probably about a minute. But this is like 1,000 frames, and I think this is the top like 75, 50%, something like that. So I was out just trying to make sure I had all my settings sort of dialed in for not using the diagonal and making sure I had my distance right and stuff like that. You can see a little prominence on the left side. There's like a double sunspot just above and to the right of it. Obviously a very prominent sunspot in the middle. So yeah, that was just taken straight from my driveway.
Now, did you color that yourself or is that? Okay.
Yeah, so I added the color. I'm using a 585 MC Pro, so it's a one-shot color. But then when I process it, it pulls it into fits, and just relatively conveniently, when I pull that into IMPPG, it only pulls the red channel, which is the most important channel, anyways. So I end up with a grayscale image, and then I just add the coloring to make it look more like, what you would kind of think of the sun.
Yeah. Very nice.
Yeah, it's great.
Okay, and I decided to do a little side by side here. So, Wes, you're first up with your rendition of the Orion Nebula.
Yeah, so I got a C-Star S30 Pro, and this is the left image is literally the first image I took with it. I pulled it out of the box, put a tripod on it, set it down, and said go. And about half an hour, and then it started to go into the trees. So that was as far as I got. But I was just really impressed with what it got in like 34 minutes, right? Like it's just 34 minutes from like Millersville with a light pollution filter. And I did nothing to this image. This is the only like just straight out of the C-Star image I'll submit because I feel like I can't take much credit for this because literally I just set it down, hit go, and this is what it gave back to me. But I was just really impressed with what it was able to pull out in just 34 minutes.
Yeah, amazing tools. They really are. Very cool. Hey, Michael, are you on this evening?
I am, Jim.
Oh, great.
So
tell us a little bit about your rendition because you're the slightly larger C-Star 50 here.
Yeah, so this is the S50, and usually in the wintertime, I like to get a shot of Orion, and so I've kind of converted to using the C-Star because it's lightweight and quick to set up, and I had this running here for just about 2 hours, and then it did its processing here. And I also kind of liked with this one, you get a nice view of the running man on top, and I just sort of like how that all kind of comes together. And I think it also didn't really blow out the center of Orion. You can kind of still see those 3 stars there, which is pretty cool. And again, just like Wes said, pretty impressive overall.
Yeah, amazing stuff. All right, and you've got another one here for us, Mike.
Yeah, this is the Perseus, sort of the double cluster, and I was able to get an hour on this one here. And this is just out in Westminster, just right in my yard. So I've got plenty of neighbors with lights on and whatnot, but the stars came through pretty well here. You can get some blues and nice oranges as well.
Yeah, that's what I love about the double cluster is those red giants in there, and your picture really picks it up nicely here. It's gorgeous.
Thank you.
Very nice. Okay, we've got another Orion Nebula here. William Coulter, are you on by any chance? I think the Vespera 2 is also another one of these AI type of telescopes. Anyone know? Is it Steve? Yeah.
Yep, it is.
So basically he did it again. This is folks doing it from their driveways, out in Columbia. 75 minutes of 10-second exposures with the light pollution filter. Now he did do, he says, post-processing in PixInsight, Sight, so he did do some manipulation with it. But again, these, I mean, I'm an old fart that remembers way back in the 70s, you would die for something like this. I mean, it was such a huge thing with the film and the tracking and oh my gosh. And now it's like we can make these amazing images. It's just incredible. So very, very nice work here. And I received yesterday a couple of these lunar photos, again, showing that C-Star isn't just for deep sky necessarily. As a member of Alpo, we got a couple images with people using C-Stars of the lunar eclipse recently. It really works well for a lunar eclipse. So, Tommy, would you happen to be on this evening to talk about these? All right, I guess not. Again, just really nice detail here in the full moon. Can't quite see the feature I was talking about, but it would be right up here for that Valles Alpes. Mr. Phil.
Yes, so this was a great, February 14th was the first warm day we had, and it was a clear sky. It was unbelievable both happened. I did travel all the way to Laurel, Maryland, in the parking lot of Company 7, and we set up there, and this is a section of, I took basically 3 areas, the whole disc, and then what's cool on here is when you try to explain to people the difference between a filament and a prominence, and that they're the same thing. And I do my white chest thing with a black phone set out there, and still, you know. But here you can see in the left there, you can see a filament that's actually coming off the edge and becomes a prominence. And this was done with my 60 millimeter Lunt in the. So this was a 60 millimeter telescope with a 2x Barlow on there, and in the double stack configuration. So it was 5 angstroms, but that looks very 3D. And when you're looking at it through the eyepiece, it was fantastic. And then you can see the other prominences down there. It was such a good day. I observed for hours.
Did your wife like it?
I said, she likes the pictures.
Okay.
That she'll look at. Yeah, to come out, look through the eyepiece. No, but in the, for those, it's great to have another HAL person here. That the coolest thing about looking at the sun is it's only about 8.5 light minutes away. So it changes and you can watch it change. And we were doing an outreach program, and the biggest prominence I've ever seen in my entire life. It would have made a photo thing, but I wasn't set up because we were in a public thing.
Right.
And, but it was unbelievable. So that was a great shot. I'm really happy with how it turned out.
Speaking of outreach and solar stuff, I know that there is like an Earth Day coming up in April.
Yeah.
And we may need a couple of volunteers. Hopefully HAL usually supports that.
Yeah.
So watch for an email that'll come out looking for volunteers for that.
Many times. I missed the last couple of years, but and it's very well attended. The sky is one, and this is just the full disc. A little bit of over processing there, but it's just trying to pull out all the features and the detail, and you see the magnetic fields and how they're messing with the plasma and the prominences, and you can see that whole chain. I showed you that on the previous picture, but you can see that whole chain of filaments going up on the left side there. That was unusual. I've been doing this since 2012, and that was not something to see all the time. And this is just a different portion of this. And I used I have the color one-shot camera, but I recorded in the monochrome because it uses all the pixels there.
Right. Yeah, this looks so 3D here,
Yeah.
almost like a wave, just great shot.
So,
And is this
you did a great job of coloring. When I color it, they don't look as realistic, so I just leave it.
Is this
There's
a flare
happening there?
A flare, that's what I thought.
So, the things off the edges are prominences. Flare is a verb, and you actually see it happen, and you see them happen all of the time. And later on, if somebody's interested, one time, unfortunately, I was the only astronomer around, but I witnessed something called the Morton wave that I've never heard anybody ever talk about. It's very, very rare. And that was back in like 2013 or so. Yeah.
Very nice work as always, Phil. Just great detail on this stuff. Okay, Chris Todd, I know you're on. You want to talk to us a little bit about your Starfront project here?
Yeah, except you're only displaying about 1/4 of it.
Well, that's what you sent me.
Oh,
I did.
there we go.
Well, that's the link. So I went out and I grabbed that because I thought, oh, well, here's the whole thing. So, okay.
Yeah. Yeah, okay. Sorry if I screwed up what I sent you. My bad. So some of you may recall my talk about remote photography from Starfront. And one of the things I mentioned after the talk was that one of the things that's cool about Starfront is there's several hundred nerds just like us. And occasionally we all get together and shoot the same thing. And so this is kind of an example of the power that you can get. This is the Helix Nebula. I forget the NGC number, sometimes called the Eye of God. And this is about 670 hours of exposure, mostly through narrowband, hydrogen, oxygen, and sulfur. There's maybe a few hours of RGB for the stars, but yeah, we were able to image really some amazingly faint outer portions of the nebulosity. And it was a fun project. There's about 16 of us. Everybody contributed from different kinds of scope. And then one processing master went in and did some magic. And yeah.
That's amazing. Just, yeah, stunning, really. Sort of thing you'd expect to see from Hubble.
Well, and that's where I think it kind of ties in nicely between Kaylee's talk and what you were just talking about. The combination of many amateurs with relatively modest equipment, but lots of time, combined with all of the advances in technology. And yeah, this wasn't that hard. And it's amazing. So yeah, another sales plug for Starfront.
All right, Victor. Victor. Oh my God.
This is the opposite of what you were just saying. This is in all ways, this is just me. And I was standing right next to my telescope so that the photons were also hitting me. But not to it's just so this was from my trip to Chile, and this was taken. It's about 7.5 hours worth of light from the Andes Mountains to the east of Santiago, Chile. And I'll talk in a lot of detail about the rig and how I carried it there and what I used, but it was basically a Nikon lens. And oh, that's right there. So it's yeah, it's a ASI 294 camera on a Nikon lens with an with a Rainbow Astro RST 135E mount. This is an unguided image. This is I could only get 1 minute exposures. It was dark enough that my histogram was off of the left side with just 1 minute exposures and at normal gain and whatnot. But anyways, I'll talk more about where I was when I did this next month. But yeah, this was the main thing I imaged over 3 nights in January.
That is a wonderful advertisement for next month's talk. I mean, it looks like an impressionist artist or somebody got some blue paint, red paint, and a black, just amazing. Just stunning. Have you sent that into Sky and Telescope or any place? Or
no.
Why not? You need to send it in.
Yes.
All right.
Okay.
I'll chew on that.
Yeah. No. All right, so I'm going to take a few moments here and talk about Jupiter. So I went out the other night, March 11th, got a picture with the great red spot starting to set. And then there's one from about 4 months earlier. And what's really cool is you can kind of take your pictures like this and deduce things about Jupiter and its atmosphere. So one of the things that you may or may not know is that it rotates at different speeds. The equator on Jupiter, the clouds are rotating faster. The rotation period here is about, I don't know, 5 minutes faster than compared to the poles. So depending on your latitude can kind of depend on how quickly it rotates back around. So what's interesting is that the Great Red Spot is actually in a zone between two jet streams. So you've got one jet stream on the northern edge of the SEB that's heading to the left here. So that's eastward. And you've got one on the northern edge that's heading retrograde westward. And that red spot kind of sits right in the middle. So it's not being carried along by the jet streams. It's kind of, if you can envision two conveyor belts and you're stuck in the middle, and you can see from the animated GIF here, it's creating the rotation here. So, but it doesn't move a whole heck of a lot. So over the 4-month period, the Great Red Spot, if you calculate it, based on the rotation, it moved 10 degrees to the east, so 10 degrees to the left. But if you look at the end of this belt here, the South Temperate Belt, where the yellow line is, and the Great Red Spot ends up over here. So that's a heck of a lot more than 10 degrees. So, that's maybe 90 degrees that the thing has moved, relatively. So what does that mean? That basically means that this belt here is sitting in a retrograde or westward moving jet stream that is much faster than the Great Red Spot's pace. So it's like you're able to, by checking the longitude and then seeing where things move, you can make deductions like this. Another one here is this spot here, this storm is called A8. And you'll notice it ends up over here in this picture in 4 months. That's even faster. So that thing's caught up in a very, very fast jet stream down here that is just booking over to the west here. And as a result, kind of not as dynamic as the sun, but over a few months or sometimes even over a couple of weeks. That's what I love about Jupiter. You can see this kind of long-term storms and how they change and relationships with one another. And with that, folks, I think that brings us to the end of our meeting. I do want to put in a plug for the HAL planning meetings, which the Zoom link is on the website. As a member, you can drop by our planning meeting, see how the sausage is made, how we figure out what we're going to do the next month or the following month. If you have ideas, drop by the planning meeting and let us know, we'll give you a few minutes and pitch your idea to us. But, it really is something that is part of the meeting structure. It's just that, we certainly don't encourage tons of people to come, but this is how we get new people involved in HAL. We need new blood, okay? We don't want to see everybody with gray hair or no hair. So, please consider continuing to stay involved in HAL. This is what makes it a great club. And one way you can do that is maybe dropping by one of the planning sessions. Other than that, we will see you April the 9th, where Victor is going to wow us all with his trip. And Bill will talk about his Mauna Kea, and I'm looking for 2 more people. So again, Kalée, I don't know if you're still on. Thank you so much. Great presentation. And I will look forward to seeing everybody next month.
My pleasure. Thank you so much for having me.
All right, guys.
Great stuff, everybody. Thanks.
Thank you.
Thanks. Good job. Bye.
Bye-bye.
It was good, yeah.
Bye.
Okay,
So Ian to win a camera in the office.
Yeah,
I still haven't had a chance to get up to. What is it that I was supposed to?
You could catch up with Victor or Jose.
Yeah.
That have keys to the observatory and can get you into the storage cabinet to get that.
Oh, so that's where.
So are you available for Saturday night?
Yeah.
Not, I was just thinking that through.
Yeah.
I'll wait until the next impromptu.
Just don't.
The other part is.
Call, whatever you want.
Yeah.
But if you reach out, Jose lives, I know it's right. So if you reach out to him or email me and I'll get you in touch with Victor and say, oh, we want you to get that camera.
I live way down in Rock Mills. It's like a big commitment.
I understand. I live in House. It's a big commitment for me to come down here too. But I'm seriously.
So I'll work it out. Yeah.
Okay.
Even if it's an impromptu, the key would still be able to get.
Should be able to. I would check with the impromptu person to make sure that yes, they should be able to.
Great session today.
Thank you.
Hi.
S30 at least doesn't let you go beyond. Because anything more than that, you start to get.
Want to make sure it
And all stuff that all that
doesn't.
can't figure out when counting.
Yeah, if there's a.
So then I don't know
Max
pictures.
that
I don't know
box.
exactly who's doing it internally. It's
Jim,
clear the line.
They put a little fan.
And this will actually give you a really good.
Oh, you're welcome. Appreciate it.
Idea what is considered like.
I need to
So,
keep this compact.
Like I said,
One
it
thing-
started getting into
one
the
source of
trees.
power
So
for
like
everything
you see
we
the
have,
tree
and
over
that
here.
is-
That's when the branches started to get out.
All right.
So then I also letting